Welcome, engineering students. Whether you're in mechanical, civil, or industrial engineering technology, mastering statics is basically your first real rite of passage. So consider this explainer your step-by-step masterclass, geared specifically toward getting you completely ready for that final exam. Today, we're unpacking the equilibrium of rigid bodies. Okay, let's ground this in reality by thinking about massive structures, like a giant Ferris wheel. It's breathtaking, right? But for industrial maintenance engineers, it isn't just a ride at a theme park. It's this massive, intricate puzzle of applied forces. These professionals absolutely rely on foundational statics to keep those awe-inspiring structures totally safe and operational. Every single beam, pin, and support literally has to be perfectly balanced. So here's our roadmap for today. We'll hit the intro to rigid body equilibrium, run through how to draw free body diagrams, figure out two-dimensional reactions, and then test it all with some concept quizzes. Let's jump right into section 1, the introduction to rigid body equilibrium. The absolute most crucial point here is that for industrial mechanisms to operate safely without, catastrophic failure, the structure can neither translate nor rotate under a load. Translation just means it doesn't slide left, right, up, or down. Imagine a factory crane holding a massive engine block. If that crane translates or rotates when it's not supposed to, you've got a total disaster on your hands. And that brings us to the mathematical anchor for our entire explainer, the fundamental equations. The sum of forces in the x and y directions must equal 0, and the sum of moments must equal 0. This is the universal language of structural stability. Really, if you understand these two lines of math, you can analyze pretty much any physical structure in the modern world. To quickly summarize this first part for your exam prep, equilibrium requires 0 translation, 0 rotation, and equations that sum forces and moments to an absolute 0. Seriously, burn these conditions into your memory, because they're the starting point for literally every calculation you're going to do in this course. All right, section 2, drawing free body diagrams, or FBDs. Following these exact steps chronologically is completely non-negotiable for problem solving. First, you have to mentally and visually detach the body from the ground and its supports. Next, indicate your external forces, and never forget the weight of the body itself. Third, indicate the point of application and the assumed direction of any unknown reaction forces. And finally, include all your necessary dimensions, because you're going to need those distances to accurately compute the moments of the forces. Think about how cool it would be to have 3D X-ray vision. If you could virtually strip away the physical steel of a 2,400 kilogram crane, what you'd be left with are the bare vector reactions. The wall supports at the top and bottom would be replaced entirely by reaction vectors. The physical weight of the load and the boom would just transform into exact downward arrows. That is exactly what you have to do on paper. Translate the real physical world into isolated mathematical vectors. Wrapping up this section, your main takeaway is to always start your analysis with an FBD. You've got to clearly separate the known external loads from the unknown support reactions before writing a single equation. A clean, accurate diagram is honestly an engineer's best friend and the secret to passing your finals. Moving right along to section 3, calculating two-dimensional reactions. Calculating specific reactions is what ensures a structure can safely support applied loads while keeping its integrity. This could be single known forces, like you'd see with a roller support, or unknown multi-directional forces, like a rough surface or a pin, or even couples from a fixed support. In modern industrial maintenance, getting this right determines whether you prescribe the correct replacement bolt or risk a joint completely failing. For exam time, remember that correctly identifying your support type is the absolute key to applying your equilibrium equations. If you see a roller, you should immediately know it's one perpendicular force. If you're dealing with a fixed wall, you're looking at two force vectors and a moment couple. Okay, section 4, let's put this all into practice with some concept quizzes. I want you to visualize a heavy rope car suspended by a single cable in an industrial facility. If this car is completely at rest, or if the hoist is pulling it upward at a perfectly constant velocity, how do we draw those forces? Think back to our equilibrium equations. Well, because the acceleration is exactly 0 in both of those scenarios, the sum of forces has to be 0. Mathematically speaking, tension minus weight equals 0. So the upward tension vector perfectly balances the downward weight vector. Constant velocity and being completely at rest actually look exactly the same on a free body diagram. Let's change up the parameters a bit. Now imagine the facility operator hits the hoist throttle hard, and the car accelerates upward rapidly. What happens to our math now? Does the sum of forces still equal zero? There's a major dynamic shift here. To accelerate upward, the tension has to overcome the weight. In our equation, tension minus weight now equals mass times a positive acceleration. We have an upward net force, which means we've officially crossed over from statics into dynamics. The upward tension arrow would be drawn significantly longer than the downward weight arrow. Conversely, what if the hoist releases tension way too quickly and the rope car drops into a rapid downward acceleration? How do our vectors respond to that sudden loss of upward pull? In this case, the downward weight vector stays exactly the same, gravity isn't taking a break, but the upward tension vector shrinks. Because weight is now greater than tension, weight minus tension equals mass times downward acceleration. This creates a net force pointing straight to the ground. All right, one last scenario. Let's say the rope is removed entirely and this heavy metal car is just resting flat on the concrete factory floor. We know it has weight, so what invisible force is keeping it from falling straight through the floor to the center of the earth? The ground is pushing back. It exerts an upward normal force that exactly counteracts the downward weight. The sum of forces in the y direction goes back to equaling zero, bringing us right back to our beautiful starting point, static equilibrium. So to summarize these quizzes, the direction of your net force vector completely dictates your free body diagram. It proves that the sum of forces equals zero is the ultimate rule for determining resting versus accelerating states. If they don't cancel out, your structure is moving, and if we're talking about a building or a bridge, that means it's failing. Before you head off to ace those engineering exams, I want to leave you with a quick thought experiment. Look around the room you're sitting in right now. What invisible reactions are keeping your ceiling from collapsing? Where are the pin joints? Where are the normal forces? And most importantly, how would you draw that free body diagram? Keep looking at the world through an engineer's eyes, and I'll see you in our next explainer.